Right, so now we're going to talk a little bit more officially about the calculus of parametric and vector functions, so throwing a new word out there. So first of all, for those of you not in physics or who haven't done physics stuff for a while, in calculus we're basically going to consider a vector to be an arrow, and it's usually defined by giving what we call the x and y components. And I can never remember how the physics department here talks about vectors or writes vectors. We are typically just going to write it like an ordered pair, but with pointy brackets. You maybe have seen I and j as representing the vector components. There's a few other ways you can do it. So the vector 3, 5 basically just means an arrow where you're going sort of 3 to the right and then 5 up. And so you're sort of starting here and heading off in this direction. So that arrow is important. It's not just a triangle. It shows motion in that particular direction. Negative 2, 4 would mean go left 2 and then up 4 from your point of reference. And so we're going to make use of this idea when we're working with parametric functions. And one thing we'll need to know is the length of a vector, and that's simply the Pythagorean theorem, just keeping in mind that when you square negative numbers, of course, you get positive numbers. And oftentimes you'll use those absolute value bars to mean the length of the vector. So the length of that first vector is the square root of 34. So when we have an object moving around the plane, we can consider it to be a vector valued function. So s with a little arrow above it means, oh, this position is a vector. The x component is a function of time, and the y component is a function of time. And basically now, the motion stuff works out the same way as it always has. The derivative of position will be velocity. It's just that we now have an x position and a y position, so we have an x velocity and a y velocity. And then when we take the derivative of the velocity function, if that box goes away here, we will get the acceleration, and again, two components to acceleration, the x acceleration and the y acceleration. That statement in green there is important. When you find the velocity vector, it will be tangent to the path of motion. And so when I go back to this picture from earlier, if you think about this object on this spiral and it's sort of moving around, when you find the velocity, as we'll do in a second, at any one of these points, the velocity will be a vector, it's an arrow, and it's going in a path tangent to the curve at that point. And so the particle's going around like this, the particle is heading in that direction at that instant. As time goes on, right, that particle is changing direction, and so that arrow is changing direction, but the arrow will always be tangent to the path at that particular moment in time. All right, what else we got? So velocity, acceleration, same as before, but x component and y component. Just like when we're doing one-dimensional motion, we've got velocity and speed. And so velocity has a direction, and so in this case it's a vector, right? So the velocity is that arrow I was just showing you on the last picture. It has size, magnitude, and a direction. Speed simply tells you how fast you are going. It does not give a direction. It's simply a number. And the nice thing is it's just the length of the velocity vector. And so if we write that out, length of the velocity vector with that little arrow up there, we do the Pythagorean theorem. What's the x component? Well, it's the x derivative. We square that. What's the y component? Well, it's the y derivative. We square that, and then take the square root of this big thing, right? So we're just doing the length of the velocity vector using the Pythagorean theorem. To find the slope, right? Slope is what it's always been. It's dy dx. It's how fast y is changing with respect to how fast x is changing. Well, the good news is we know how fast y is changing. That's dy dt. And we know how fast x is changing. It's dx dt. And so the slope of a parametric equation, and this is definitely an important item, is the slope of y, the derivative of y with respect to t, divided by the derivative of x with respect to t. And so in essence, you are just finding the slope of the velocity vector, right? The slope of the velocity vector. All right, hopefully I'm not going too fast here. Of course, you can pause the video as needed. got a couple more components to this. And so one is we'd like to know how far objects traveled. And in one-dimensional motion, we did that, and we know that in one-dimensional motion, we have the difference between displacement, right? And displacement is when I just integrate velocity, and that tells me how far it moved in net, right? So ending position minus starting position, how far it moved in net. That does not take into account back and forth motion, and so in one-dimensional motion, when we wanted to figure out how far the particle moved in total, we will have to take the integral of the speed. And we definitely did that. It's been a little while. And so we'd integrate the absolute value of velocity, and that would tell me the total distance traveled in either direction. Right? The good news is it's basically the same thing in parametric motion. The displacement's a little tricky, and we'll talk about that at some point, but it turns out in this case, total distance traveled is easier. It's just the length of the parametric curve, and we're going to do the same thing we did in one-dimensional motion. We're just going to integrate the speed. And so what's the integral of the speed look like? Well, we just figured out the speed. It's the length of the velocity vector, and so we just integrate this. As you would guess, this is often a very, very messy function, a messy antiderivative to take because you've got the square root, the squares. Very high percentage of the time you would just do this integral on your calculator, right? You would take the derivatives, you'd plug it in to the appropriate formula, and then take that integral using Math 9. This is sort of cool because we now can find the length of a curve, which is how far that particle traveled. You may remember that we haven't actually done this in other types of curves. And so when we look at a parabola, for example, back in Algebra 2, in calculus, we have never talked about how to find the length of a parabola like this. It's not a straight line. We can't just use the Pythagorean theorem. It turns out we can use the same parametric idea, just that in this case, y is going to be a function of x, and x is just going to be x. And so it's sort of like turning a regular function into a sort of simple parametric equation. X is x, and then y is the function of x. And so if I don't have a parametric function and I want to find the arc length of it, I'm just going to take the derivative of x, but that's just 1, and then the derivative of y, but I have a name for that. That's f prime. And I'm going to plug it into the formula we just saw. But 1 squared is 1, and then I take this derivative and square it, and then I take the square root and integrate, right? And so this will find the length of that curve over the given interval. And so now if I want to find the length of the parabola, I can do it. All right, one last thing, and then you'll have a chance to do a little practice. And so the last thing is the second derivative of a parametric function. This is one of those things sort of like the Lagrange error estimate, where it's a little tricky. The good news is it'll probably show up on like one multiple choice question or something, but we may as well get that one right. And so how does the second derivative of a parametric function work? And so the trick to the second derivative, right? And so it's the second derivative of y with respect to x. And so the second derivative, that means you take the derivative of the derivative, right? So we're taking the derivative of the derivative. And we know what the derivative of y is in a parametric situation. It's dy dt over dx dt. And so how do we take a derivative with respect to x? We basically have to take the derivative of the top, this thing, with respect to t. And so I'm going to take the derivative of that original derivative with respect to t, and then I have to take the derivative of the bottom, I have to take the derivative of x with respect to t again, right? So it's the derivative of the original thing, in this case the derivative with respect to t, and then divide it by the derivative of x with respect to t again. I realize that explanation was maybe a little muddled, but we'll go through an example here in a second and it should make sense then.